this was a circuit that I asked you guys to analyze, or at least most of you guys to analyze, for exam 1 last quarter. It was one that an overwhelming majority of you missed almost all of it, but definitely 19 and 20. I think the correct response rates for that was somewhere in the ballpark of 16 to 17%. So we are going to use this example problem to do two things. One, refresh you on how nodal analysis and all that kind of good stuff works, because we're going to be doing a lot of it in this class, because some of the circuit analysis techniques that we are going to be learning and the circuits that we are going to be analyzing rely almost entirely on nodal analysis and not on mesh analysis. And then we are going to effectively get the results that we are looking for without doing any analysis whatsoever. So here. Let's analyze this guy. So our circuit in question looks something like this. We have a 2 amp source connected in parallel to an 18 ohm resistor. Here we have a 3 ohm resistor, a dependent voltage source supplying a voltage of 4 Vx. A 16 ohm resistor, a 10 ohm resistor, current source direction down of 3 amps. We have a common node down here at the bottom. And then we have a 7 ohm resistor up here. And the voltage drop across the 7 ohm resistor, positive polarity on the right, is our voltage Vx. We are asked to determine, for the exam, we were asked to determine what the voltage Vx is. The power absorbed by the 2 amp source, and the power supplied by the dependent source. And it was my intention of creating a circuit with 5 meshes to force you guys to try to do nodal analysis on this guy. That being said, you could have done mesh analysis because this mesh current is 3 amps, this mesh current is 2 amps, and then that eliminates 2 unknowns if you thought that far ahead. We're going to approach it using nodal analysis. Part of the reason why we are going to approach it using nodal analysis is because, one, that's probably the technique you're least comfortable with, so it's a good idea to have a review. Number 2 is our circuit simulation tool works explicitly using nodal analysis. It does not use mesh at all. So if we're going to be using circuit simulation tools that utilize nodal analysis, again, using nodal is going to be a good thing. So for this particular problem, let's say that our reference node is this bottom node. And from that, this node over here on the left, we'll call node A, which has a nodal voltage of VA. This node here in the middle will be node B, which has an associated nodal voltage of VB. And this node on the right is node C, which has a nodal voltage of VC. So, because this circuit has a voltage source, it contains a supernode. So the supernode will be between node B and ground. So we will only have a voltage relationship expression. We will not have to do Kirchhoff's current law because we never do Kirchhoff's current law at a node or supernode that contains our reference. So our voltage relationship equation in this case is simply going to be VB, or VB minus 0, is equal to 4 Vx. So while we have this dependent source in mind, let's go ahead and write the expression for our controlling variable as well. So how would we express Vx, the voltage drop across our 7 ohm resistor, positive polarity on the right, in terms of our nodal voltages? VC minus VA, absolutely right. We could substitute this relationship into our voltage relationship equation, and that would give us -4 VA minus VB plus 4 VC is equal to 0, which will be one of our 3 equations that we'll use to solve this guy. Our other 2 equations will come from applying Kirchhoff's current law at node A, and another will come from applying Kirchhoff's current law at node C. So KCL at node A is going to look like -2 amps. So that's the current flowing. Let me make this super clear here. I want this current flowing to the left, this current flowing down, this current flowing to the right, this current flowing up, add them all together, set them equal to 0, right? So the current flowing to the left is -2 amps. The current flowing down is VA over 18 ohms. The current flowing to the right is VA minus VB over 3 ohms. And the current flowing up through the 7 ohm resistor is VA minus VC over 7 ohms. Set all these guys equal to 0. This is equation 2. And then finally, we have KCL at node C, where we are going to be looking at this current plus this current plus this current plus this current, all add together to make 0. So starting with the current going left and going counterclockwise, we're going to have VC minus VB divided by 16 ohms plus VC over 10 ohms plus 3 amps plus VC minus VA over 7 ohms is equal to 0. That's our third equation. And we can solve these guys to figure out what VA, VB, and VC are. So it's been at least 2 weeks since you've used your calculator. So break it out and get unrusty. Cheston, you'll be happy to know I actually broke down and bought one of those Casio 991s over the break.
Oh, nice. How do you like it?
Haven't even taken it out of the package yet. Yeah. Anybody got any results for me yet? Alexis. Negative 16.518 volts. That's what I got. What'd you get for VB? And what'd you get for VC? All right. So those are what I got as well. So they're correct. Not because I got them, but because I've tested it. So now that we know what those nodal voltages VA, VB, and VC are, we can pretty easily, well, I say pretty easily, my hope was that it was supposed to be pretty easy to figure out these three quantities up here that we need. So for instance, Vx, we already know to be simply VC minus VA because we had to use that to solve this guy, right? So since Vx is VC minus VA, if we do that simple operation, we're going to get, sorry, that doesn't look like an equal sign, negative 5.706 volts. Now, to calculate the power absorbed by the 2 amp source, what do we need? We need the current flowing through the 2 amp source, which is obviously 2 amps. And because we want the power absorbed, we want that 2 amps of current to be flowing into the positive polarity terminal, right? So I'm going to call this voltage V 2 amps, right? So that the voltage drop over the 2 amp source is oriented in such a way that the current flows into the positive polarity terminal and out the negative polarity terminal, so that V2A times 2A gives me this power. That makes sense. I'm just using the passive sign convention. So how does that voltage V2A relate to any of our nodal voltages? Negative VA, that's it. So we can say that P2A absorbed is simply 2 amps multiplied by negative VA, and that's going to give us 33.0 watts. To get the power supplied by the dependent source, I need to know the voltage drop across the dependent source, which is simply 4Vx, and the current flowing into the negative polarity terminal. So I'm going to say that the current flowing into the negative polarity terminal, this guy right here, I dependent, is simply this guy plus this guy using Kirchhoff's current law. Everybody okay with that? So from that, P dependent supplied is 4 VC minus VA multiplied by VB minus VA over 3 ohms plus VB minus VC over 16 ohms, which gives us 48.486 watts power supply. All right. So that took us 20-ish minutes to solve for those 3 parts and all that kind of good stuff. What I'd like to do now give you guys a minute to open up your laptops and all that jazz, because we are going to draw this circuit in LT Spice. And we're going to simulate it. And we're going to compare the simulated results to the results that we got analytical. This is going to be a portion of most of your homework assignments, okay? Where you will simulate the circuit and then compare your results to those of the simulation. So this is a way to check whether or not you got the question right. If the answers don't match, then that begs the question, did I work the problem wrong or did I simulate the problem wrong, which is a whole other bag of cats that we'll worry about in a little bit, okay? All right, since this is probably most of your first time using this particular software package, I'm going to go fairly slow. And if you get lost or you didn't catch something, by all means, stop me and I'll go back through and re-explain it, okay? So the first thing that I'm going to do is open up a new schematic because I'm going to be creating a new circuit. Now up here, hopefully you guys can see me waving my mouse and all this kind of jazz up here, is where we can pick circuits, or excuse me, pick components and all that kind of good stuff from. So there is a ground node component that we can easily just drop in. This guy right here is for labeling a network, and we are going to use that in a moment. This is for resistors, and then one over is capacitors, inductors, diodes, and then this guy that looks like a, I guess that technically be an AND gate, right? It's been a hot minute since I did any digital design. That AND gate icon is not for digital logic gates, it is for general components. So that's where we get our voltage sources, current sources, and all that kind of good stuff from. Op amps, transistors, not for this class, but for many of your later classes and all that kind of good stuff. And then I want to say the hand icon is for moving stuff around. And then there are also things to, you know, rotate, mirror, all that kind of good stuff. So let's start by dropping some resistors into our guy. So I'm going to start with this resistor R1. And because I'm nitpicky and want things to look nice, I'm going to press escape and then start wiring things up. You do not have to do this by any stretch of the imagination, but I always try to give myself 2 units of wire as leads for the resistor in both directions to wire things up. So if this resistor R1 is our 18 ohm resistor, then I'm going to put some wire over this way to put our 3 ohm resistor. So the resistor, when you press the resistor button, comes out oriented vertically like this. To rotate it, simply press Control R. And now it's horizontally oriented. And I'm going to wire up some more bits. I know that this thing right here down is where my dependent voltage source is supposed to go, and we'll get to that in a moment. But I can put it as a wire for now just to leave that space. Now I'm going to place my 10 ohm resistor. Now I'm going to place my, sorry, that was the 16 ohm resistor, and this will be the 10. My apologies. All right, so right now this guy's a little too big for me to put the rest of the stuff on here. So you can scroll your mouse wheel up to make things smaller, or if you have a touchpad like I do, you can just pinch your fingers together to make it smaller, spread your fingers apart to make it bigger, and then I can simply just drag it around wherever I want it to. So I'm going to wire up that 7 ohm resistor on the top now. So I'm just putting a wire all the way across, and then just going to drop that resistor there in the middle. And I have all the resistors taken care of. So let's take a moment here. One, to let you guys catch up. If you have any questions or anything, by all means ask. And then we're going to figure out how to enter actual values. Yes.
A way to go back to like the last thing that you had selected, so you don't have to re-click like resistor wire. Actually, you can press like R on the keyboard for resistor and then see faster like L for stuff.
I didn't even know that. So let's see what happens if I press the R key. Oh, I just get a resistor. I'll be damned. That's pretty easy. Huh. All right. So we have this resistor network taken care of, or at least I hope we do for most of us. To enter in the resistor value, we simply mouse over the resistor and right click, and it should pull up a menu like this. We can actually select resistors, which I practically never do because a part number for a resistor and all that kind of stuff doesn't make a whole hell of a lot of difference. The resistance value that we put in here will be measured in ohms. So if we put 1, it's 1 ohm. If we put 1K, it's 1 kilo ohm. If we put 1 M, it's a milli ohm. So it does not matter if you put capital M or lowercase m. LT Spice can't tell the difference. So if you ever want a mega ohm, you need to type in MEG, and then it will give you a mega ohm resistance and all that kind of good stuff. So this resistor R1 is supposed to be an 18 ohm resistor. So I'm just going to type in 18. Notice here, we can also include a tolerance percentage because real resistors have tolerances. Good resistors have tolerances of around 0.5%. Really crappy resistors have tolerances of around 10 to 20%. We can also put in the power rating so that we could use this circuit analysis tool to see how much power is being dissipated in our circuit and see whether or not we are going to burn any resistors out or anything like that. So pretty handy for when we get into design projects and for simulating things when we get into senior design and all that kind of good stuff. For this class, though, we're just going to leave those 2 fields blank. So I'm going to press OK, and then I'm going to go around the circuit and enter the resistor value for everything else. Now, to be clear here, I am mousing over the middle of the component and right-clicking. If I right-click where it says R3, it gives me a different box where I can just mess with that text. That's how I rename resistors and all that kind of good stuff, which for the intents of what we're doing right now is completely unimportant. Technically speaking, I can right-click on this text R at the bottom and put in the value as well, but it can be confusing because it's, again, just a simple text editing thing. So my preference is mouse over the middle of the component and get the actual full-on box for putting in all the parameters. So I have all of my resistor values set up correctly. The next thing I'm going to do is wire up my current sources. So I'm going to go from this node here where the 3 and the 18 ohm resistor are connected and give myself a chunk of wire and kind of wrap it around like so. I'm going to do something similar over here between the 4 and the 16. And then, now that I have those wire leads in, I'm going to press the component menu. and I'm just going to type in the word current. I don't even have to type all of it in. Current sources are represented by current. By default, the current source is oriented with the direction down. Since my 2 amp source on the left is direction up, I could either put it down and put -2 amps, which I'm not going to do, or I can simply rotate it twice, Control R, and now it's pointed in the correct direction. I'm going to place my current source over here on the right. Since it's direction down, I'm going to rotate it twice to put it in the right orientation and then press escape because I've placed my 2 current sources correctly. So to enter in the value of the current source, we simply mouse over the middle of the element and right click. And it asks us for a DC value, which is what we're going to be using. But before we simply put in 2 amps here, I'm going to click on this advanced button and show you guys a couple of things. Okay. So built into LT Spice is the ability to have a current source or voltage source, all of the sources work this way, that generate a series of rectangular pulses, where we have the initial current, the current when the device turns on, how long it takes for the device to turn on, how much time it takes to go from its initial current to its max value, how much time it takes to fall from its max value back down to the initial, how long it's on, and then the period of the cycles and how many cycles we want, all that kind of good stuff. So we can make just rectangular pulses all day long. We can also do sinusoidal currents and voltages, where we get to choose a DC offset, the amplitude of the sinusoid, the frequency of the sinusoid in hertz, the delay time before the sinusoid starts, theta, which is the phase angle, phi, which I don't remember, and the number of cycles. I will tell you, the sinusoidal source literally gives you a sine function. Everything that we do is based on a cosine function and all that kind of stuff. So to make things match up, you will need to put the phase angle to be -90 degrees to kind of fix it, but it's available. Then we have exponential sources. I don't remember what SFM stands for. PWL, so this is effectively you put in a series of lines and all that kind of stuff, and it uses that to create a source. Or you can just use a table and have it iteratively go through all the different things. Okay. So very, very powerful here. These are all the different types of functions we can do. Excuse me. Over here on the right-hand side, we can put in our DC value. Underneath that is for small signal AC analysis. So when we get into filters and all that kind of good stuff, these are the current sources we're going to use. And then we can also mess with parasitic properties like make it a non-ideal current source effectively. So let's cancel out of this guy and go back to the original menu and just type in the number 2. And then for this guy over here, and find my mouse, here we go. We put in the number 3. And we only have a couple of things left to do. All right. We need to put in a dependent voltage source. And LT Spice does not differentiate between current controlled voltage sources and voltage controlled voltage sources. They're all lumped into the same thing. So because we want a dependent voltage source, we type BV. BV stands for behavioral voltage source. And when we drop this guy in, we can see that the voltage it supplies is equal to a mathematical function that we get to define. Okay, so for us, that's supposed to be 4 times Vx. So we need to define what the voltage Vx is first. So I am going to say that the voltage Vx is the drop over this 7 ohm resistor with the positive polarity terminal on the right and the negative polarity terminal on the left. How I'm going to force that to happen is I'm going to choose the left terminal of my resistor to be ground. I don't have to do this, but this is just going to make things a little bit easier to read when we get the output of the simulation, okay? So I'm choosing this node to be our reference point. And what I'm going to do now is I'm going to label a node as Vx, where this label is counting as a positive polarity terminal with respect to ground. So this is exactly how Vx was defined in our original problem. Positive polarity on the right, negative polarity on the left. What's significantly different though is our reference here, it is now here, as opposed to the bottom of the circuit. So what that means is that our nodal voltages VA, VB, and VC are going to be vastly different because they have a different reference. But the voltage drop across this resistor is going to be the same. The power absorbed by this current source is still going to be exactly the same. And the power supplied by this dependent source is exactly the same. So I'm choosing a different reference than what I did in my analytical solution because I want to make the simulation give me the answers in the easiest possible form, okay? The last thing that I need to do, excuse me, is right click here. And where it says value, I need to change this function. So I want it to now say V is equal to 4 times V open parentheses Vx. So how LT Spice interprets things, it's interpreting Vx as a nodal voltage. And so it's actually interpreting this text signature here as me labeling a node. That's a better way to put it, me labeling a node. And so I'm saying the voltage that's being output by this dependent source is 4 times the voltage at node Vx. So I press OK. And now we are ready to simulate. So the first thing I'm going to do is go to edit simulation command because this is a DC circuit. We want to do a DC operating point simulation. So I went up here, simulate, down at the bottom, edit simulation command. You can also click on this guy right here, and this is where you can enter in what are called SPICE directives, where you can just type .op and put it on the thing and it'll do it just as well. And now I'm going to run a simulation. So we can see here that the voltage at node Vx is negative 5.706 volts, which is exactly what we analytically got, right? The powers aren't anywhere on here right now. And honestly, I'm not sure if we could force them to show up there. But after we run that simulation, if we mouse over any of the components, it gives us some information down here at the bottom. So for instance, it says that at the DC operating point of this circuit, this resistor R5 is carrying a current of negative 815.18024 milliamps, and it is dissipating or absorbing 4.6516 watts of power. Now, unfortunately, with the DC operating point analysis, it does not tell us what the direction of the current is. I'll talk about how we can figure that out in a moment. But if we put our mouse over our 2 amp source, we can see that it is dissipating 33.035 watts of power, which is exactly what we got from our analytical work. Similarly, if we mouse over the dependent source, we can see that it is absorbing negative 48.846 watts, which is the exact same as supplying 48.846 watts, right? So our simulation gives us the exact same results as our analytical solution. So this is a fantastic way for us to check our work. All right. I fully expect you guys to use this to check your work for your homework assignments and all that kind of stuff. There's practically no reason for any of you to never make not make 100 on any of the assignments if you understand how to use LT Spice. Brandon.
Instead of labeling VX, I noticed that if you hover over the nodes, it's already pre-assigned a name. Can you use that instead of?
You absolutely could. So let me delete this and delete that ground. So what Brandon observed is absolutely correct. When you mouse over a node, it tells you this is node N001 for this instance. So what it does is it starts with the top leftmost node. That's node 1, 2, 3, 4, 5. This guy down here at the bottom should be node 6. Maybe I was wrong. Wait, 1, 2. Where's node 2? Okay. Yeah. 1, 2, 3, 4. Yeah, there we go. All right. Anyway, if we tried to run this simulation right here, we're going to get an error. Unknown node VX, that's fine. Actually, that's not the error I was even talking about. The error that I was expecting is since we don't have a reference assigned, it won't run a simulation. So let's prove that since this is node 1 and this is node 2, if we right click in here, I'm going to change this text to say VN002 minus VN001. I'm redefining what VX is in terms of the nodes that were already assigned by LT Spice. Press OK. There it goes. This circuit does not have a conduction path to ground. Please flag a node as ground. So let's put ground as this bottom node here, how we looked at the circuit earlier, or how we analyzed the circuit earlier. And so effectively, it's giving us almost the exact same results that we got in our analytical solution, but in a slightly different order because node 1 does correspond to node A, but node 2 is what was node C, and node 3 is what was node B. Now we could literally just go back and label them VA, VB, and VC and make it exactly match what we were doing. If we close this out,
Why do we get different values? Why do we get different values when we get before?
we're getting the same values, we're just getting them in a different order.
When we did it last one, we got like -6 and -5.
So for VA, we got -16.518, which is that. For VB, we got -22.825, which is that. For VC, we got -22.224, which is that.
How about when you ran it with the ground and top of it?
Because so we're getting different values because we put a different reference. So we're doing everything with respect to the bottom node having a potential of 0 volts, as opposed to having the top left node have a potential of 0. So that they fundamentally have to be different because we're using a different reference. But let me close this out right here real quick. The power absorbed by the 2 amp source didn't change at all. The power absorbed by the dependent source didn't change at all. The voltage drop over R5 or the 7 ohm resistor also didn't change. We would just have to simply take this nodal voltage at node 2 minus the voltage at node 1 to give us that VX, and it would still give us -5.7 blah, blah, blah. I set the simulation up earlier to give me VX directly instead of making myself do any math because I'm lazy, right? So you can set the simulation up to give you the answers you want directly, or you can set the simulation up to match your analytical work, and then you can verify all the steps that way. Either way works. All right. So LT Spice can do a whole heck of a lot more than just simple DC operating point simulations. So this is where we've started. And for a lot of what we're going to be doing over the next week or two, really all we're going to have to do is DC operating point simulations. When we have to do anything different, I'll walk you through that as well. But I just wanted to give you kind of a brief introduction as to how this guy works. So all of this has been recorded. So sometime likely this weekend, actually, no, I guess I need to do it tomorrow because I'm going out of town this weekend. So tomorrow morning, I should be able to edit and upload this video. If you have any questions or want to go back and refer to it. If you got anything you want to ask me right now, we technically still have 15 minutes before class is over. So feel free to ask any questions you have. If not, I'm done talking for the day. See you guys later. Brandon.
Is there a way to add dimension to this program, as in like adding a length to your wires, size, that way you can account for internal resistance of wires?
I'm not sure. How I've always done that is literally just putting a resistor there and setting the value of the resistance based on the math that tells me what to do. So like my simulations that I do for the job I work of out of Bossier, I'm doing effectively, it's like an RL circuit on steroids because I have to account for the resistance and inductance of all of my wires, all of my portions of my bus bar and all that kind of stuff, how they couple to each other and all that jazz. And I model all of those things just using simple ideal resistors and inductors where I did the math to figure out what those values should be. So I'm not saying LT Spice can't do that. I'm saying I don't know if it can or how to do it if it does have that
I
capability.
guess it wouldn't be that necessary